Hey everyone! So in this video I like to cover a few ideas from geometry that'll be useful for us and add some context to the class. Hey everyone! So in this video I like to cover a few ideas from geometry that'll be useful for us in this course. And so the first idea I like to cover is this idea of similar triangles. So two triangles are similar if the three angles in one of the triangles they're identical to the three angles in the other triangle. And so here I've got an example of a pair of similar triangles, and that's because if I look at the angles in this triangle, we see this 98 degrees appear in both of the triangles. We see this 32 degrees appear in both of the triangles, and we also see this 50 degrees appear in both of these triangles. These two triangles have identical angles, and so we call them similar. And so what's special about similar triangles is that if you take the ratio of two corresponding sides from one triangle and the other, they're going to give you the same ratio no matter which two sides you pick, which corresponding pairs you pick. And so what I mean by that is that if I look at this side length that's opposite the 32 degree angle in both of these triangles, so this 5 centimeter side length and this 10 centimeter side length, they're corresponding sides because they're both opposite that same angle 32 degrees. And if we take their ratio, 5 centimeters over 10 centimeters, we get 1/2. And so what I'm trying to say here is that no matter which corresponding sides we take between these two triangles, when we divide them, we should get that 1/2 every time. And so if I look at, maybe let's do these corresponding side lengths. So I'm missing a side length here, but we know that if we take these two corresponding side lengths and we take their ratio, so 9 centimeters divided by something that we're missing here, we know we're going to get that ratio of 1/2. And so what should I divide 9 by to get 1/2? Well, this ought to be 18. And then similarly, if we look at this side length opposite this 50 degree angle, and we take their ratios, so let's take 7 and we divide it by this unknown side length. Well, we know we're going to get 1/2, and here that denominator, well, it better be 14 to get that ratio of 1/2. So this ought to be 14 centimeters. And so that's the idea behind similar triangles, is that if we take two corresponding sides and we look at their ratio, we're going to get the same ratio every time. And so we can use this to determine side lengths for missing side lengths for similar triangles like we did here. Something else you may have noticed is that if you look at the side lengths of the first triangle and then you compare them with the side lengths of the second triangle, well, the side lengths in the second triangle are all double the side lengths of the first triangle. Right, so really, we can kind of imagine that to go from this first triangle to the second, we just really multiplied all their side lengths by 2. This is another way you can kind of define similar triangles, is that there's some number you can multiply to all of the side lengths of one triangle to get all of the side lengths of the other. So let's go ahead and use this idea of similar triangles to figure out the missing side lengths in these two triangles below. And so if you're feeling up for it, I definitely encourage you to pause the video and try this example out yourself. And when you're ready, we can go over this together. So the first thing I notice here is that there's this missing angle actually. Right? So there's this angle here that we're not aware of. And one fact about triangles is that when you add up all of their angles, what you should get is 180 degrees. And so I know that 45 degrees plus 60 degrees plus this missing angle, I'm just going to put a box there. It should come out to 180. And so 45 plus 60, well, that's 105 degrees. Plus this missing angle is equal to 180 degrees. And then subtracting 105 degrees from both sides tells us that this missing angle, well, that's 75 degrees. And so here, maybe I'll just write that down as 75 degrees. And if we look at this other triangle here, well, it also has an angle of 60 degrees, also an angle of 45 degrees, and so that missing angle is also 75 degrees. And so these two triangles, they're similar. They have identical angles. And so now we can use this idea of similar triangles to take the corresponding sides and notice that all of their ratios ought to be the same. And so let's sort of identify the corresponding sides. So so here, here's my angle of 45 degrees, and it's got that side length opposing it of 12, and then here's my angle of 45 degrees. Here's my opposite side length of 36. And so these, they're corresponding side lengths, and so the idea behind similar triangles says that if we take the ratio of these two side lengths, we're going to get the same ratio as if we take any other pair of corresponding side lengths. So well, we get 12 over 36, and that's the same as 1/3. And so here, another thing we might notice is that we have this angle of 60 degrees, and the opposing side to that 60-degree angle is 45 for the second triangle, and we're missing it for this first triangle. And so this unknown side length, when we take this ratio of that unknown side length and 45 degrees, or not 45 degrees, 45 as a side length measurement, well, we better get that ratio of 1/3. And so what should the side length be? Well, maybe this is a little bit less clear than our previous examples. We could just try and solve this equation, multiplying both sides by 45. We get 45 over 3, making this unknown side length, well, 45 over 3, that's 15. So that's this measurement here. Okay, so we have one more side length to figure out, and that's this side length corresponding to our angle of 75 degrees. So here we know that we've got 17 as a measurement of the side length of the first triangle, and we've got a missing side length as a measurement of our second. So we should get 17 divided by this missing side length is going to give us 1 over 3. And so we can solve this equation, but really all of these denominators are just 3 times the numerator, and so 3 times 17, well, that's 51. And so there we have it. We have all of our missing side lengths. That was a task that we wanted to complete, and we've done it. Okay, so there are 2 more ideas I'd like to talk about that'll be really important for developing the ideas of trigonometry. That'll show up just time and time again throughout this class. And then so here, maybe let's just jump into one of these examples. So this problem says, find the missing side lengths and angles in the right triangle below. And so there's a right triangle in this picture, but there's also this triangle that the right triangle sort of sits inside. Maybe let me just outline it real quick here. So this triangle, maybe let's just talk about this one for a moment before we dig into the right triangle. A moment ago we said that when we add up all of the angles, the 3 angles in our triangle, any triangle we have, they should add up to 180 degrees. And so if there is 60 degrees here and 60 degrees here, well, to get to 180, we still need 60 degrees more. And so this top angle here ought to be 60 degrees if we're looking at the bigger triangle at play. And so whenever we have a triangle that has identical angles, all 3 angles are the same, 60 degrees, we're looking at an equilateral triangle. An equilateral triangle is any triangle which has 3 of the same angles. And it's also the case that in equilateral triangles that all of the side lengths are the same. And so the fact that we know that this side length is 2 inches, that tells us that all of the other side lengths here, when we're looking at this equilateral triangle, are also 2 inches. And so here at this bottom side length, there's 2 inches here. That's the measurement of the side length of this equilateral triangle. Not for the right triangle that we're interested in, but this is going to help us. Okay, so here maybe I'll sort of erase some of this picture here. Okay, so we're really interested in finding out the side lengths and the angles for this right triangle. And notice that it really makes up half of this equilateral triangle. And so it feels reasonable to say that this top angle will be 30 degrees. And we can actually say that more precisely, or get there a little bit more precisely. We know that this is 60 degrees, this is 90 degrees. And so this top angle here, well, we know that it's going to need to add with 60 degrees and 90 degrees to get to 180 degrees. Right, so this is 150 degrees plus this missing angle is 180 degrees. And so subtracting 150 degrees from both sides gives us 30 degrees. So this is 30 degrees. This is an example of a 30, 60, 90 triangle. We're going to see these sorts of triangles all the time in this class. And so, notice that the bottom side length, that leg length there for this right triangle, it's half of the side length of the overall equilateral triangle side length. Right, so here, this side length is going to be 1 inch, and that's because it's exactly half of this entire, the 2 inches here. And so now this last side length that we need, this missing side length here, maybe I'll label it B. Well, how can we figure out the measurement of this missing side length? So here we're dealing with the right triangle, so we can use the Pythagorean theorem. We know that if I square the leg length and add it to the square of the other leg length, well, it's going to be the same as the square of the hypotenuse, so 2 squared. And so this makes the equation come out to be 1 plus b squared is equal to 4. And so subtracting 1 from both sides gives us that b squared is equal to 3. And so if b squared is equal to 3, well then b is going to be the number that squares to 3, which is the square root of 3, actually plus or minus the square root of 3. But because we're talking about a side length, we're just going to deal with this positive side length. It doesn't really make sense to talk about a negative side length here for this triangle. So here b, the missing side length, that's the square root of 3. So this is one of the 2 actually special right triangles that we're going to look at all the time in this class. This is going to be called, or we're going to refer to it frequently as a 30, 60, 90 triangle, because the angles in this triangle are 30, 60, and 90. And one thing I want you to notice is that the side length opposite the smallest angles is the smallest side length. So this 30-degree angle, opposite this 30-degree angle is this smallest side length of 1 inch. And then opposite our largest angles is going to be our largest side length, the hypotenuse in this right triangle. And then opposite our middle sized angles are our middle side length. So the square root of 3, I think that's roughly 1.7 or so. Don't quote me on that though. Okay, so this is a special right triangle. This is actually not the example of this 30, 60, 90 triangle we're usually going to see. Usually we're going to deal with the special right triangle, the version of this 30, 60, 90 triangle with a hypotenuse of 1. And so maybe let's take a look at that 30, 60, 90 triangle for a moment. So here, maybe I'll just draw it out. So again, let's look at this 30, 60, 90 triangle. And here, we're looking at one with a hypotenuse of 1. And so let's make sense of what the side lengths of this 30, 60, 90 triangle with a hypotenuse of 1 are. There are a few ways we can do this. We can sort of play the same game and imagine that it's sort of half of an equilateral triangle, and it would, the logic would work out exactly the same. I mean, maybe we can just do it real quick. Right? This side length is going to be half of the total side length of this this equilateral triangle on the side length on the bottom, and that would be, well, that would be 1/2, right? If this is half of an equilateral triangle of side length 1 all around, then that bottom leg length of the right triangle will be 1/2. And then we can use the Pythagorean theorem again. Here maybe, let's just do that. We'll have 1/2 squared plus, here I'll call this again b. b squared is equal to 1 squared. And 1/2 squared, well, that's 1/2 times 1/2, that's 1/4. Plus b squared is equal to 1. And then subtracting 1/4 from both sides gives us b squared is equal to 1 minus 1/4, and we can rewrite this as 4 over 4 minus 1/4, right? It's to subtract two fractions, we ought to have the same denominator. And I know that 1 is the same as 4 over 4, right? Any number divided by itself is going to be equal to 1. And then when we subtract two fractions with the same denominator, well, we just subtract away their numerators, right? So 4 minus 1 gives us 3 in the numerator over 4. And so this makes b equal to, well, plus or minus the square root of 3 over 4. This makes it plus or minus. It turns out that if we take the square root of a fraction, well, that's the same thing as a fraction of consisting of square roots. So here, if I have the square root of a over b, this is the same as the square root of a divided by the square root of b. So we can break apart square roots across fractions. And so this gives us b is equal to the square root of 3 over the square root of 4. And finally, that gives us that b is equal to plus or minus the square root of 3 over 2. And so here, maybe I'll just write that down now. So b is equal to, in this case, the square root of 3 over 2 if we're talking about the side length for this triangle. And so this is an example of a right triangle that I really want you to commit to memory. So sometimes when people teach trigonometry, there's a lot of memorization that goes on, and really we can avoid a lot of the memorization just by remembering this 30, 60, 90 triangle. So this is one of the two things I really want you to sort of internalize and memorize. So here, if we're looking at a 30, 60, 90 triangle, the hypotenuse is side length 1. The short side is going to be half of that, and it's going to be opposite the short angle, the smallest angle. And then the longer leg length, well, that's going to be the square root of 3 over 2. So there's one more example of a special right triangle that I really want you to commit to memory. I'm not the biggest fan of memorizing things, but really memorizing these two special right triangles will save you a lot of memorizing down the road. And so this other special right triangle I want to talk about is 45, 45, 90 triangle. So here, maybe I'll just draw it out. Of course, there are many 45, 45, 90 triangles that are all similar with one another, but let's look at the example with a hypotenuse of 1. This is going to be the one that appears the most frequently in this class. So here I'll just label the angles 45 degrees, 45 degrees. So here for this 45, 45, 90 triangle, this is an example of what's called an isosceles triangle, a triangle with two identical angles. And just like it was the case for equilateral triangles, which had 3 identical angles, they had 3 identical sides. Here we have 2 identical angles, we have 2 identical sides as well. So although we don't know these side lengths here, maybe I'll label them x and x, we know that they'll actually be the same measurement. And so that's why I've labeled them with the same variable. And so here, let's try and make sense of what the value of these side lengths are. Again, we can actually use the Pythagorean theorem. Even though we're missing 2 side lengths, they're the same side length, so we're only missing one piece of information here. We can work through the Pythagorean theorem and solve for this value x. All right, so the Pythagorean theorem says that if I take one leg length I squared and I sum it with the square of the other leg length, we get the square of our hypotenuse. Well, x squared plus x squared, that's 2x squared. And 1 squared, that's just 1. And so solving this equation gives us, x squared is equal to 1/2. And so, I want x, not x squared, so let's take plus or minus the square root of both sides. And like we said earlier, we can break apart fractions along square roots. So here I can rewrite this as the square root of 1 divided by the square root of 2. Well, the square root of 1 is just 1, right? So this is plus or minus 1 over the square root of 2. And this is a sufficient answer, actually. We can stop here and write down that x is equal to 1 over the square root of 2 when we're dealing with these side lengths. But another way you'll frequently see this value, this number, written out is without a square root in the denominator. And one way we can achieve that or get there is we can multiply this fraction by the square root of 2 over the square root of 2. This is called rationalizing the denominator. And when we do that, we get that x is equal to, well, plus or minus the square root of 2 in the numerator, right? 1 times the square root of 2 is the square root of 2. And then the square root of 2 times the square root of 2, well, that's squaring that square root of 2. And that's just going to give us back 2 itself. So here, our side lengths for this 45, 45, 90 triangle with the hypotenuse of 1, our side lengths are, well, the square root of 2 over 2 and the square root of 2 over 2. So this is another example of a right triangle that I really want you to commit to memory.